Let us start today's lecture. Let us draw the circuit of a three-phase induction motor. In the stator side, we have Y connection as we saw in our previous lecture. This is the neutral point. This is suppose phase 1. That means phase 1 supply is given here, and this is another point, and this is the third point. So all these 3 points are supplied by three-phase supply. So let us give three-phase supply. Phase A is connected with P1, phase B is connected with P2, this is P2 for example, and phase C is connected with P3. We have three-phase supply here, and this is the internal resistance R1 of the stator winding and X1 reactance of the stator winding. This is also R1 X1 R1 X1. Now if we draw the short-circuited rotor winding circuit, it will have a similar pattern. We are considering it's having Y connected configuration. But for this case, the other sides of these configurations are shorted. For squirrel cage type motor, for one rotor type, this shorting is not done directly, rather the connections are taken through slip rings. We may short the other side, or we may connect any external resistance with this. So this is rotor resistance R2, and this is rotor reactance X2 prime. This is the reactance of the rotor side at standstill, because the reactance value at standstill and the reactance value under running condition won't be the same. For our convenience, any notation in the stator side will be denoted by 1, like R1, X1, and any notation in the rotor side will be denoted by 2, like R2 and X2 in this way. So the stator side can be taken as the primary side and the rotor side can be taken as the secondary side, and there is no connection. The power is supplied in induction method, that's why it is called induction motor. So we have R2 here and X2 prime here, as this is balanced load. We have balanced load in the stator side as well, and we have R2 here, X2 here. It will also be our general notation that whenever we'll use prime, that will represent that value in the rotor side under standstill condition. So from our last class, we know the induced EMF at the rotor side E2 equal to S into E2 prime. What is E2 prime? As we have 2 here, so this is the rotor induced EMF. As we have prime here, so this induced EMF is considered under standstill condition. So under running condition, the general value of E2 equal to S into E2 prime, where S is the slip. If we consider the rotor current frequency at standstill is F2 prime. From our previous lecture, we know this F2 prime equal to supply frequency at standstill. So under running condition, the rotor current frequency will be rotor current frequency under running condition, that will be F2 equal to S into F2 prime. Now the value of rotor reactance under running condition X2 equal to twice pi f L. Actually, this will be the twice pi f2L, the current frequency in the rotor side under running condition, which can be written as twice pi s into f2 prime L. If we take s out, we can write twice pi f2 prime L, which can be written as s into x2 prime. From here we can write where x2 prime equal to, which can be considered as rotor reactance at standstill. So we have got E2, the rotor induced EMF, equal to S into E2 prime. F2, that means rotor current frequency, equal to S into F2 prime, where F2 prime is equal to the supply frequency, and X2 equal to S into X2 prime, where X2 prime is the rotor reactance at standstill condition. For all cases, S denotes the slip. As both in the stator side and the rotor side, we have balanced load, so we are considering the induced EMF for per phase case and reactance for per phase case, and all other values for per phase case. So this is the induced EMF E2 at the rotor side, which depends on the magnetic field cutting, and the cutting depends on the speed of the rotor. That's why E2 equal to S, which depends on the speed of the rotor, into E2 prime, which is the induced EMF at standstill, which has a fixed value. Now we'll figure out the equation for rotor current per phase. Since the motor represents a balanced three-phase load, we need to consider one phase only. The conditions in other two phases will be similar. So at standstill, the rotor current per phase, will be equal to, as we are considering standstill current conditions, so let's name it I2 prime. I means current, 2 means rotor side, prime means at standstill. So at standstill, the rotor current per phase I2 prime equal to this EMF divided by this complete impedance. So we can write here EMF per phase at standstill is E2 prime. So I2 prime will be E2 prime divided by this impedance. E2 prime divided by this impedance, that is Z2, which can be written as E2 prime divided by Z2 equal to root over R2 square plus X2 prime square. Because we are considering standstill condition, so the reactance will be X2 prime, and the rotor power factor let us write as cos phi 2 equal to R2 over root over R2 square plus X2 prime square. I hope you know this equation. The rotor power factor depends on this resistance and reactance value. So we have R2 here and X2 prime as inductive reactance. So the power factor can be calculated using this equation, R2 divided by R2 root over R2 plus X2 prime square. Actually, what happens, we have R2 value in this direction, X2 value in this direction. This is the power factor angle phi 2. So according to the Pythagoras, This line will be root over r2 square plus x2, let's write x2 prime square. So in order to get this cos phi 2 value, we need to divide r2 by this root over x r2 square plus x2 square. Will get the cos phi 2 value that will give us the power factor. So this is the rotor current per phase under standstill condition. Next we'll figure out the rotor current under running condition. Under running condition at slip S. Whenever we'll say that the rotor is in under running condition, that rotor must have a speed. For that particular speed, we'll get a particular slip value. So we'll generalize the equation under running condition for slip S. So the rotor current per phase will be I2, as it is under running condition. That's why I'm not putting that prime notation, equal to, under running condition we cannot take S equal to 1 where we'll get E2 equal to E2 prime. Rather we need to consider E2 where E2 equal to S into E2 prime. Under running condition the induced EMF in the rotor side is E2 and E2 should be divided by Z2. It's better if we write Z2 prime here, then we can differentiate. So E2 should be divided by Z2, which can be written as E2 S into E2 prime divided by root over R2 square plus X2 square. Again we can write S into E2 prime divided by root over R2 square plus X2 equal to S into X2 prime. S into X2 prime whole square. So this is the current equation I2 under running condition. When the rotor is at a standstill, the value of S will be equal to 1. If we put value of S equal to 1, we'll get the standstill current per phase. So if you put the value of S equal to 1, we'll get exactly this equation, which represents the rotor current under standstill condition. So this can be treated as generalized equation for both running condition and standstill condition. For standstill condition, we know the value of S equal to 1. If we put the value of S equal to 1, then we'll get the current that is the standstill current. Now the rotor power factor under running condition. Cos phi 2 at standstill condition, it's better to write cos phi 2 prime, so that this phi 2 will represent the power factor angle under running condition, equal to R2 divided by root over R2 square plus S into X2 prime square. Next, we'll start our discussion on rotor torque. As we know, torque is a measure of the force that causes an object to rotate about an axis. In our case, we will measure the torque for the rotor as it is the only rotating part. At the very beginning, we need to know why the rotor torque in an induction motor is developed. Suppose this is a three-phase induction motor, stator part, and this is fed by three-phase supply. Inside this hollow part we have the rotor. These are the side view for rotor part, and we have conducting bars. Whenever we give three-phase supply, then there is a creation of rotating magnetic field. Whenever this magnet starts rotating in any direction, the flux cuts the rotor bars and EMF is induced. Due to that EMF, current starts flowing through the rotor bar. So the induced EMF in the rotor side is directly proportional to the flux. And due to that induced EMF, if we have higher amount of induced EMF, then current flowing through the rotor bar will also be higher. So we can say the torque developed in the rotor side is directly proportional to this magnetic flux. So we can write torque tau developed by the rotor is directly proportional to number 1 magnetic flux, and also number 2 the current flowing through the rotor, because if we have higher amount of current flowing through the rotor, then the force exerted on the rotor bars will be higher, so eventually the rotor torque will be increased. So we can say the rotor current, and as the rotating magnetic field is rotating, sometimes north will be here, south will be here as it is rotating, so the current produced in the rotor side will be AC. So that's why we need to consider the power factor as well. So it is also proportional to the power factor of the rotor circuit. So we can say this torque developed by the rotor is directly proportional to the magnetic flux. If you denote it by phi, remember this is the notation for magnetic flux phi. This phi and this phi, they are not same. Here phi is the angle, power factor angle. Here the magnetic flux is denoted by phi. Well, next time I'll write theta here instead of writing phi. Then there will be some difference. Okay. For the time being, you keep it in your mind that they are not same. So tau is directly proportional to the phi into I2 prime. Why did I take I2 prime? Because we are considering motor is at a standstill at the very initial moment when motor starts. At that moment, the torque produced in the rotor side is called starting torque. So we are considering the starting torque. So we may write it. This is the consideration for starting torque. That starting torque tau is directly proportional to phi I2 prime. That means current at a standstill into cos theta 2 prime. Here remember this theta 2 prime is another notation of our previous phi 2. Actually phi 2 prime is here. That means this is the power factor angle at a standstill condition in the rotor side. So this is phi 2 prime. Let's go to next page. We got starting torque tau is proportional to phi I2 prime cos theta 2 prime, as we wrote in the previous note. So it can be written as tau is directly proportional to phi. What is the value of I2 prime? I2 prime is the per phase current. If we consider rotor impedance per phase Z2 prime, that is at standstill, equal to root over R2 square plus X2 prime square. Rotor current per phase will be I2 prime equal to E2 prime, that means induced EMF in the rotor side at standstill divided by Z2 prime. How did we get this? We know from our previous slide. This is the E2 prime at standstill, and this is the Z2 prime. So the current per phase will be E2 prime divided by Z2 prime, which can be written as E2 prime divided by root over R2 square plus X2 prime square. And the rotor power factor power factor cos theta 2 prime can be written as R2 over Z2 prime equal to R2 over R2 square plus X2 prime square. So the starting torque can be written as, instead of I2 prime, we can write E2 prime divided by root over R2 square plus X2 prime square into, instead of cos theta 2 prime, we can write R2 divided by root over R2 square plus X2 prime square. All these at standstill condition. So the starting torque of the motor can be written as tau is proportional to phi into E2 prime R2 divided by R2 square plus X2 prime square. From here, let's come here. This phi is directly proportional to the E2 prime. Why? If you increase the magnetic flux, the induced EMF in the rotor side will be increased for the same amount of rotation. If you reduce the magnetic flux, the induced EMF in the secondary side will also be reduced. So we can say phi is directly proportional to E2 prime, that means induced EMF in the rotor side at standstill. So we can write tau is proportional to E2 prime into E2 prime into R2 divided by R2 square plus X2 prime square. From here we can write tau equal to K, where K is constant, into E2 prime will give us E2 prime square R2 divided by R2 square plus X2 prime square. This is the equation for starting torque. We finish our lecture here. We'll continue in the next lecture.